we'll just wait for more people to join, that's all. Start around like 10:45, let's say, right? I think 10:45 is a good time. I have access to your comment section also. In case you have any doubts, you can put it in the comment section. Is it too noisy here or is it fine? I hope it's not very noisy. Noisy here? I hope it's not very noisy. Uh, I don't think we can start with age for now, because like it might be a bit like difficult for other viewers to understand. I don't think we can start with age for now. I mean, we'll just go on the regular order, I feel. If you join in like around half an hour later, I think we'll be doing HR at that time. So hopefully that's fine, right? Okay. Okay. Yeah. Hopefully that's good. Okay. Yeah. Okay. Like we just have very less viewers for now, so we'll just wait for a couple of more viewers to join, and after that, I think we can get started. Right. I think we can get started for now. I'll be a bit slow since like all this might be new for a couple of people, so I think we can be a bit slow also. Now, the point is like this, right? So basically, we can do the following thing. We like if we go look at question A. Question was like we have three starts with letters A, B, and C, and basically we can kind of swap any of the two letters. So the question is like, can you get the string ABC if you do some swap, right? So if you look at my solution, I think it was very straightforward. So we are allowed to do at most one swap, right? So if initial string was ABC, then it's fine. If initial string was BAC, you could swap the B and A characters. Then also we are good. If your initial string was ACB, then you could swap the B and C characters and we'll be good. And likewise for the fourth option also. So in those cases, we are just outputting yes, and anytime else we are outputting no. So is that clear? Okay. If you have any doubts, you can again ask in the comment section. I think that should be fine. But let's keep going. So let's go to problem B. So I'll quickly explain problem B. Problem B goes like this, right? We have some like a bunch of digits basically, and so what they're saying is basically we can add 1 to any of these digits, and we want to maximize the product. So this is actually quite interesting. So let's think about this, right? To which digit should you add 1? And intuitively, I mean, it's pretty clear. You should probably add it. Like there should be some pattern, right? I mean, you can't just like randomly add it anyway. And it turns out that you should always add it to the minimum digit. Now, this is just a claim which I'm making, and this is no reason to be true. But I'll kind of try to prove to you why this is true. Oh, also, maybe digit is probably a bad term, I guess, because like we could, like if you have a 9 also, we could add 1 to it and make it 10, and 10 is not a digit. So I guess the terminology here is like not very good, but anyways, we'll still stick with it. So I'll kind of give you a small proof. Hopefully my screen is visible, right? Okay, that's good. So if you look at problem B, initially we have some digits, right? P1, P2, P3, all the way up to Pn, right? Let's say they are all in increasing order. Now, which of these will be bigger? I'll tell you two things. Will it be this thing or this thing? So the second thing I have is actually something like this, right? Now, if you look at this clearly, this thing is bigger. Actually, why is this thing bigger? Because it's the original number plus P2, P3 all the way up to Pn, and that definitely will be bigger than the thing on the right, because the thing on the right is the original number plus P1, P2 all the way up to Pn, right? So the thing on my left is definitely bigger. That's why we always add 1 to the smallest number and not the largest number. So hopefully that's clear, and that's what we did essentially. So we just added 1 to the last number and we did away with it. I'll show my solution for it. Oh, I'm also counting some zeros here. It's some extra stuff which I did. You don't have to do this. This piece of code should be more than enough to do whatever we wanted. So just take all the input, just sort all the inputs to the smallest number, add 1, and just find the product and just output it. So that's about it. So is that clear? Any doubts? Okay, that's pretty good. So let's keep going. I'm assuming there are no doubts. If you have any doubts, you can always ask in the comment section. If my audio or something is not clear, you can just put it in the comment section again. Hopefully that's fine. So let's keep going to problem C here. So problem C is this, right? So we have a bunch of rings. And they're asking us to like essentially calculate our score if you have a bunch of arrows or whatever, right? Yeah, some arrows kind of thing. So it's essentially some kind of let's say a dartboard, right? We have some kind of dartboard thing, and what we are doing is we have points for each of the rings basically. So this thing has some points. This will have like 5 points, I guess. The next thing has 4 points, so and so on and so on. So I think it's fairly straightforward. We just check the index basically. So like we just look at the position of the point. Now I did some complicated implementation, but on second thoughts, if you have a point x comma y, right? So first thing you have to realize is that which disk we are in is determined by the max of x comma y, right? The minimum doesn't matter, only the maximum matters. Like for instance, if I look at all the points with the 5-point range, like if I zero index it from like one of the corners, all of them will be 0 comma 1, sorry, it will be like 5 comma 5, 6 comma 5. Oh, I mean, if 1 comma 1 was one of the corners, then the center point will be like 5 comma 6, 5 comma 5, 6 comma 5, and 6 comma 6. So the point I'm trying to make here is only their maximum matters, and basically nothing else matters. Okay. So already this is pretty interesting. So essentially what we can do is we can think this to be the origin. So let's keep the origin here. If we keep the origin here, we can like essentially take the maximum, because if you have some point over here, the thing that decides the points is the larger of these two. So that's the maximum and not the minimum. So we just care about the max of x comma y and basically nothing else. Now I have max of x comma y here, right? So now I think it's fairly straightforward. After we have shifted the coordinates, once we have shifted the coordinates, we just like basically like do the following thing. We just like if the max of x comma y, that's somewhere between 0 and 1, that means we just output 1. Somewhere between 1 and so if it's between 0 and 1, we output 5. If it's between 1 and 2, we output 4, I guess. And we keep going. So I think that's trivial enough. So I'm not explaining that too much. I guess my implementation was a bit painful. Like I subtracted 4.5 and I shifted the origin in a different way. Probably is a better implementation, but I think this also works. So is that clear? Okay. Oh, someone in the chat is asking when I'll do G. I do G eventually in like 10 minutes or so. So but not right now. Okay. So let's keep going. If you look at problem D, I'll explain that also. So they're saying we have essentially a strip of paper that is n cells long, and in one operation you can color k consecutive cells and make them all white. And how many operations do you need, right? I feel this is also a fairly peaceful question. So the question is like this, right? We have some big like string kind of thing. And in this we have some black indices. So I'll shade all the black indices. So this one is black, maybe this one is black, maybe this one is black, right? And every time we're only shading, like making the next k colors white. So like maybe we could shade it here and make these k colors white, like these k cells white. Maybe one more time we could make these k cells white, etc. It keeps going like that. Now what is the best thing to do, right? Now let's think about this. Like if you look at this in a greedy way, look at the very first black cell, right? Now if you look at the very first black cell, we have to color it in some way. So if you look at the very first black cell, coloring it something like this, is that a good idea? Like if your box of width k look something like this, is that a good idea? No, right? Because essentially we are wasting a lot of white color. It might also work obviously, but it's not very optimal. So like you can kind of intuitively see that if you have like a window of length k, we want the window to start at the black cell basically. So does that make sense? So so that's one thing, right? Now this window may or may not contain other black cells. The point is we don't really care about it. We don't care about it because anyways all this will become white. So if the first black cell was some index, let's call it I, we immediately just look at the index I plus k minus 1, because that like the window of width k would have become white whether you like it or not. And then again we just recursively do the same thing basically. So I hope that thing is clear. And I mean like this, like you keep finding like black cells and coloring the next k segments, and we don't care what happens to the k segments, etc., etc. So we just keep going. So that's the basic idea for this problem. So I'll quickly show my implementation also. I think the implementation was fairly easy. So we have two integers n and k. We have some string s. We just take if a particular index is b. If it's b, we increment our count variable, and we just like move, like we just move to the current index plus k minus 1. Like we just move k minus 1 indices to the right. So hopefully that thing is clear. Okay. Now okay, right. Now let's keep going. Okay. Any doubts in D, by the way? If you have anything, you can ask in the chat box. I have access to the chat box. Hopefully that's fine, right? Okay. I'm also audible, right? I hope I'm audible. I think my audio should be fine, but that's fine. Yeah. Okay, just confirming once. Okay. So let's look at problem E once. So problem B was a nice question. I think it was binary search. It had little edge case I had to catch. I didn't see that the first time. But I'll explain the question. You can pause it and have a look through it. I'll give you a couple of seconds. Okay, just give you a couple of seconds. Okay, I am assuming all of you have gone through the question. If not, you can just pause it and see it later. I think that's fine. The point I'm trying to make here is like we okay, so we have an aquarium, right? So the problem is simple enough. We have W amount of water, and like we have a bunch of I guess they call it coral reefs, I guess corals. So corals have some height like this. Now we are allowed to choose a height h, like we choose some height h basically like this. Now anything above the height h we don't do anything, but anything that's below the height we just have to submerge it with water. So like what will be how much water we have? We can calculate water needed, right? So let's have a look at water needed if the height is some h. So what will be the expression for the water needed? If you think about this, it's just summation of all I such that I'll just write it down first. Okay, 1 second. Should be something like this, I think. Yeah, and we want A to be less than h, less than or equal to h, right? So this is how much water we need. So we just look at the indices where A is smaller than h. If you have a particular index where A is smaller than h, we take the difference and we fill it with water. So that's how much water we need for a particular h. Now the conditions, we want this to be smaller than W, right? We want this to be less than or equal to W, and let's see the way you can achieve that. There is a small caveat here in the sense that like we are given W, like we are given how much water we can have and we need to find h, and it's pretty intuitive that we have to do binary search, right? I hope it's intuitive, right? I mean like the solution turns out to be binary search. So like let's do binary search for all values of h between 0 and some like very large number, let's say 10 power 18 or something. So yeah, I mean that's basically what we have to do. We just have to do binary search for the correct value of h. We see if a particular value of h takes more water than we need or less water than we need. If a particular value of h needs too much water, then we can't achieve that value of h. Otherwise, we are fine. So let's just have a look at my implementation. Like that's the basic idea. I'll also explain what went wrong in my first submissions. Let's have a look at that also. But if you look at this, the idea is simple enough. This checking is fairly straightforward. It's like the variable s here denotes how much water we need for a particular value of h, and we're just checking if s is smaller than or equal to x. X is how much water we are allowed to have, and then we are just doing blunt binary search in the sense that we just look at the lower index, the higher index, and we just plainly search through it. So hopefully that idea is clear over here. Yeah. Okay. As I was saying, the caveat here is as follows. So if x was like 10 power 9, because the bounds of x could be 10 power 9, and if some a was also 10 power 9, right? Like if one of the correlatives was actually 10 power 9, then actually how will it look? That particular peak will have a height 10 power 9, and all the water above it, you have this much water above it, that will also have 10 power 9, leading to a total height of 2 times 10 power 9. So that is my issue in the first place. I did binary search only from 1 till 10 power 9, and that gave me a bunch of issues. And then once I did it from like 1 till 2 times 10 power 9, the answer passed. So yeah, so that's where it went wrong in my E submission. So hopefully that's fine. Let's keep going. So let's look at problem F also. I think problem F was pretty nice. So problem is fairly straightforward also. I think you can have a look at the question. The problem is like this: we want a contiguous subarray such that all the consecutive elements like divide each other. That's one thing. And one more thing is we want the sum of all the fruits in that particular subarray to be less than some k. And the question is, what is the maximum sum you can collect? I'll just show my code here and explain, because I think that will be a bit easier in this particular case. Hopefully the question is clear, right? If you have any doubts, you can ask in the chat box. That thing is always there. Okay. So what we do is fairly straightforward. We just keep track of the start, the current sum, and the best sum we can have. Now, basically what we do is we add the current index to like wherever we are right now. We just add the correct index, the current value. We just add the current like fruit number here. Now after we are checking something actually. Like what are we checking? We are checking if the current sum is greater than k. If it's not greater than k, we just increment the starting index. So like we can like okay, I mean I'll demonstrate in a better way. So we have some starting index in our array, and we have some ending index also in array. Ending index is what we are iterating over, is ith index. Now we just check if the sum of elements in this that's greater than k. If it's greater than k, we have problems. So we just increment the start variable to start plus 1. So it's basically some kind of 2 pointers kind of thing. That's one way to think about it. Now apart from this, there's one more thing to think about. What is that actually? Like we have to check the divisibility condition also. If it is divisible, we are fine. If something is not divisible, then what do we do? Like if a particular index is not divisible, we actually restart our summation. So if some index is not divisible by the previous index, we say we start summing up here. We say we just start summing up at this particular index, and we keep going. So hopefully nothing is clear. Right? I don't think any doubts in this question. Okay. 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 Someone in the chat wants implementation of E. I'll show that in a minute. Yeah, I'll show that in a minute or two. We'll finish F and then go to E. But hopefully E problem is clear, right? So E problem, what I'm doing is fairly straightforward. So first thing I'm doing is I'm just checking if the sum of all the elements from start to I that's bigger than k. If it's bigger than A, I keep decrementing my indices till it becomes smaller than k. That's one thing. One more thing, if something is not divisible, then like if a particular hi is not divisible by hi plus 1, then what do? I'm saying I'll start my array here. So I say start equals I plus 1 because like my array now starts at this particular index, and I'm also setting the current sum to be equal to 0 because I mean I just started my array, so obviously I won't have any sum. So hopefully that thing is clear. My implementation is also basically the same thing. I think it should be clear. You can always pause the video and watch this if you have any issues, but yeah. Okay. Someone in the chat asked me to show the implementation of E. I can show that. Yeah. E was binary search. I did it using binary search. I'm not sure if there are any other methods to do this. There probably are, but anyways, I did only binary search. So I'll go through the implementation once. So this check function here, what does this check function do? Check function basically takes in A, takes in I mean, A is all the vector of the coral heights, takes in X also. X is how much water we have, and H is the current height, and it returns a Boolean value. So like the variable S here, which I've highlighted right now, that variable S is basically how much water we have, how much water we need in order to fill the entire coral reef. We're checking if that's less than or equal to X. So that's first thing we are doing. Now comes the binary search part. So we take L equals 1 and R equals some big number, and we start doing binary search. In that case, what do? Like we take H to be some L plus R plus 1 over 2. Like H is the midpoint basically. We are checking if there, like we're just checking it. Now if we are checking it and it works out, we just set L equals H. If it doesn't work out, we move the right index and we bring it to H minus 1. If it does check out, we move the left index to H. So is that clear? If you have any doubts, you can again ask in the chat box and I'll explain it. I think we can keep going for now. So I'll go to problem G. Problem G was nice, I think. Apparently it was a very nice question in the sense that, I mean, it took me a while to get the answer, so I thought that was pretty good. So we'll go to E. So G. So the G question goes like this, right? We have a string made up of A and B. So two things we can do: we can convert AB to BC, or we can convert BA to CB. Okay. Now first thing is this, right? Once we get a C, we can't do anything. Like in the sense that we are basically done for, because we can't do anything with a C. So like if we start with an A, we are converting that to a C, but not in a very direct way, some indirect kind of way. So I'll yeah, okay. So going to problem G, I'll take a very specific case of A, B, right? We have something like this. What can you do? Think about this. We have some AB here, so we can convert that to BC. So we can make this A, B, C. Now we can again do one more operation, make this A, B, C, C. We can do one more operation, make it A, B, C, C, C. We can do one more operation, make it B, C, 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 right? So we're able to do 4 operations in this case. Also, let's think about something else. If you have something like this, right? B, A, in that case, what can we do? We can do the same thing, but this time we'll be moving the B to the right, but it's exact same idea. The basic approach is the same. Okay. So we'll keep that in mind. Now, so in this case, what is the basic idea? The idea is simple enough, right? If you have something like A, B, A, right? Now, here we have 5 A's, here we have 3 A's. Now, you can only move B in one direction. What do you mean by that? I'm saying if I move B to the right, I'll introduce a C somewhere. And once I introduce a C, I can't do anything. So if I have a structure like this, I can move B either to the left or to the right, but I can't do both. Like I don't have the freedom to do both. I can only either move to the right or to the left. So because of that, we conclude that in this particular case, at least, it's better to move to the right, because if you move to the right, you'll be getting 5 numbers. But if you move to the left, you'll only get 3 numbers. So we move B to the right in this particular case. So this is one interesting sub case, right? Now let's assume there are no consecutive B's in the entire array, and our array looks something like this. So if there are no consecutive B's, it looks something a bit like this. Right? Okay. So we just count how many A's are there in each piece. There are 4 A's here, there are 3 A's here, there are 5 A's here, there are 4 A's here, right? Now, in the biggest question we have to ask right now is, in which direction do we make the B's move? Like, I mean, the B's kind of move in some way, to put it in an intuitive way. Like as they keep getting replaced by C's, they move in a particular direction, and you can't change the direction of a B. That's one way to think about it. Clearly, you can see that in this particular case, like for this first B, it's better to move to the right. For this B, move to the right, move to the right. Why am I saying this? Because here there are only 3 A's, so you can kind of exclude this segment. So we always exclude the segment which has 3 A's, and like we do, like for everything else, we move like everything to the right of the minimum segment to the right, and everything to the left of the minimum segment to the left. So like if you have some minimum like minimum number here, like minimum length segment of A's, In that case, what do we do? So excluding this, we choose to ignore this, ignore all the a's inside this. We can't do anything about it. But all the a's to the left, we pick all of them up, and all the a's to the right, we pick all of them up. So hopefully nothing is clear. Now we can do a bit better. Well, what can we do better? If you have two consecutive b's, then what can I say? If you have two consecutive b's, regardless of anything else, I can make one b move to the left and one b move to the right. That means I can pick up every single a. So since I can pick up every single a, that's actually very good, right? Because I'll be able to pick up every single a, and that's basically the best I can do, because like I can't do better than picking up every single a, because my total score is upper bounded by how many a's I have. So if I have two consecutive a's, I'll be able to pick up every single a, and that's about the solution. So I'll explain the solution quickly. Okay. So like we just keep track of how many a's are there. So this variable a just keeps track of how many a's are there. We just check if there are any consecutive b. If there's any consecutive b, we just output the number of a's. Otherwise, we do the thing I told you about. So we keep track of like each of the segments. Among all the segments, we find the minimum length segment. So what do we do exactly? I just like just bluntly founded all the segments. I sorted the array of my segment lengths. In that, I just excluded the smallest segment, and every other index I just found out its value, and I outputted that. So is that clear? Any questions in this? You can stop me right now. I can answer. It's not exactly easy to come up with, but I think it was fine. It wasn't too bad. Let's look at F also. Okay. So you can, I'll pause the screen for a while. You can read through H for like 1 or 2 minutes. Okay. Right. Okay. So let's just think about this. So let's keep going. Like problem H was actually very interesting. I think the problem is straightforward. I think I can just explain the problem to you, because it's not too hard to understand. We have a graph basically. This graph has special property. The graph has n vertices. It has n edges, right? What does having n edges mean? Having n edges is a very interesting property. So if you have n edges, there will be one cycle for sure. If there are n minus 1 edges, there will be a tree. If there are n, also they gave that it's connected, by the way. They are saying any two pair are connected. So if you have n minus 1 edges, it will be like a tree, right? So this is what you'll get if you have n minus 1 edges. But if you have n edges, then what will happen? That means you need to close the cycle at some point. So you will definitely have a cycle. So if you have n edges, that's basically the same thing as a cycle, but it has only one cycle, like not more. Only one cycle. You definitely can't have any more cycles. So that's one more thing to keep in mind. Yeah. Okay. So the problem statement is like this, right? So there are two people, Marcel and Valerie. I'll mark Marcel by M and Valerie by V. So the problem goes like this, right? So basically, Marcel will try to chase Valerie. Marcel will move in a particular direction, and like Valerie can essentially act accordingly and try to evade Marcel. So that's the basic idea of this. So think about the conditions when this happens. It's fairly straightforward. So we decided that our graph has a cycle, right? So I'll just draw some big cycle here. Now think about this, right? When can they evade basically? Well, they can evade if, let's say, Marcel was over here and Valerie was over here. Like if Marcel moves here, Valerie will go like this, etc., etc. Like they just keep looping the entire circle and they never catch each other. So the claim I'm trying to make is only if you enter the cycle, the moment you enter the cycle, they can't catch each other, because like they'll keep like looping the cycles. But of course, something might happen. What might happen? So our structure looks like this, right? There are no more cycles. So there is one more arm coming like this. There are many more arms coming out, but there is one arm in which Valerie is present. Okay. Now think about this. Only if value tries to, like only if value enters the cycle, they can escape, right? But the catch here is, like this particular point might be reached by Marcel faster than Valerie. So if Marcel comes here first instead of Valerie, then definitely Valerie can't escape. So basically the conditions, when will Valerie escape? So let's call this point as close point. What is close point? So Valerie belongs in some basically tree kind of thing. Like so Valerie is a separate segment. Oh, this could have more branches, by the way. I think that's fine. But the point is, Valerie belongs to some kind of thing like this, and the nearest cyclical point, the nearest point in the cycle from Valerie, let's call that a close point. So when will Valerie escape? Like Valerie will escape. Valerie escapes, we say yes, by the way. Valerie will escape if the distance between B and close point. What is B? B is Valerie's position, by the way. If this is strictly smaller than the distance between A and close point, what is A? A is Marcel's initial position. In that case, they can escape, but in any other case, they can't escape. So that's just a claim I'm making. But I mean, you can prove this also, and it worked out for me, so it will be correct only. My implementation had a lot of issues, so that's why I got a bunch of wrong answers. But I'll show you the correct implementation. So I have two functions, right? The first DFS is just cycle detection. So I have a global vector called cycle, and I have some code that basically detects a cycle. So I'll explain this. So I'm taking all of my inputs here. I just make an adjacency list and stuff like that. After that, what I do is I basically find the cycle. Like I find where is a cycle. There definitely will be a cycle, as I've told already. There has to be a cycle somewhere. So I just keep track of where is the cycle, and I throw all of them in a set called current. So what is current? Current is a set of all the nodes which belong in the cycle. And as I told you already, it's fairly easy to detect cycles using some cycle detection algorithm. It's just a single DFS path should be more than enough. So in our DFS pass, what we do is we kind of start at a particular node. In DFS, if we encounter a node which you have met already, that means it has to be a cycle, right? Like if we come across a node which you have visited already, the only way that could happen is if there is part of a cycle basically, and that's kind of what we are checking here. So hopefully that thing is clear. But yeah, so I mean there is standard template code for cycle detection. You can just copy paste that. But the more interesting part is we calculate all the distances. How will we calculate distances from like we want the distances from this point, right? We want the distance from like basically Marcel and close point, and we want the distances from like from Valerie and close point. So we can just find that using some single Dijkstra pass. So Dijkstra is fairly standard, I think. So you just run one Dijkstra from A and run one Dijkstra from B, and that will let you know what is the distance to the close point. I mean the minimum distance to close point. So hopefully that's clear. So what this DDFS function does is it's basically a Dijkstra pass. So we just do like a greedy Dijkstra kind of thing. Even BFS would have worked. Even BFS is the same thing. It would have worked, but Dijkstra also works. So that's pretty good. So now we have all the distances here. We just find what is the close point. As I told you, what is close point is the essentially the point in the cycle that has the shortest distance from A. We find out what is the close point. That close point might be A itself, by the way. Like if A itself was part of a cycle, then it would be the close point, but our claim still holds. If the distance from A to close point is greater than the distance from B to close point, we output yes. Otherwise, we output no. And that's about the solution. So I hope that was clear. Okay. Oh, Anurag says thank you. Welcome. Hopefully you did enjoy it. But yeah, that's pretty good. Okay. So I think we are done with editorial today. Are there any more doubts? I mean, if you have any doubts, you can ask in the chat box. I'll close at like 11:18ish. You have like 2 more minutes to ask one. Okay, I'll wait for a couple of more minutes. I mean, worst case, you can also add a comment at the end of this, or you can maybe put in the chat box also. Anything works, but like, okay, that's fine, right? Okay. Okay, right. If there are no more doubts, I think we can wrap up for now. So thank you very much for watching. Make sure you subscribe and like our videos. Saying that, I think we have to cut for now. So see you. Bye.